All right, for any of you heading into a manufacturing processes course, you're going to learn pretty fast that bending a simple piece of sheet metal perfectly is a classic challenge. I mean, it looks easy, but getting it right is pure engineering. Today, we're going to walk through the entire playbook from the theory on paper to the hands-on lab work to show you exactly how it's done. Our whole process is broken down into 4 key parts. First, we'll get to know our main opponent, the metal itself, and just how stubborn it can be. Then we'll use math to predict its every move. After that, we take our theory and put it to the test in the lab. And finally, we'll use a digital twin to prove our work. So first things first, why is bending a piece of metal so much trickier than, say, just folding a piece of paper? On the surface, it seems pretty straightforward. You just apply some force, right? Well, in reality, there are 2 major challenges that stand in the way of getting that precise, clean bend you're looking for. The first challenge is what's called the material's rolling direction. That's basically the direction the metal was stretched when it was made. If you try to bend with that grain, you risk getting these ugly, structurally weak cracks. For a clean, strong bend, getting that orientation right is absolutely critical. It's non-negotiable. The second, and honestly, the more subtle challenge is something called springback. You see, metal has a memory of its original flat shape. So after you bend it and let go, it'll try to straighten itself out just a little bit. And it's this tiny, springing back that can completely ruin a precise angle. So how do you defeat these problems? You don't guess, that's for sure. To beat things like springback, engineers use very specific calculations to outsmart the metal before a single tool even gets turned on. For our project, the mission was crystal clear. Take this 1.5 millimeter thick aluminum sheet and bend it to a perfect 105-degree angle. Not more, not less. The whole game plan really boils down to 3 critical steps. First, you predict exactly how much that metal is going to spring back. Second, you calculate the overbend angle you'll need to cancel that out. And third, you pick the absolute right tool for the job. Now, the theoretical analysis for this project predicted the aluminum would spring back by, get this, just half a degree. Seems tiny, right? But believe me, that tiny amount is more than enough to make your final angle wrong if you don't account for it. So to fight back against that half degree of springback, the math showed that the punch, that's the tool pressing the metal, had to bend the sheet to a sharper angle, 104.5 degrees. This overbend is the secret to landing right on target. The tool you pick is also key. A 12 millimeter V-die was chosen to do something called air bending. All that means is the sheet is only supported on the edges and never actually bottoms out in the die. This gives the operator maximum control over the final angle. Okay, the math is done, the tools are picked, the blueprint is complete. Now it was time to take all these numbers off the page and see how they hold up in the real world. And now for the fun part, the lab work. The team set up the press brake with that specific 12 millimeter V-die and a clearance of 2.25 millimeters. The aluminum sheet is in place, and it's ready for the press. After the press does its job, just eyeballing the angle isn't good enough for engineering. Nope, the team took a high-resolution photo and used digital measurement software to get a precise, undeniable reading of the final angle. And here it is, the moment of truth. The final angle, measured digitally, came out to 105.473 degrees. So how close is that? We're talking a deviation of just 0.45% from that 105-degree target. That is an incredibly small error, and it proves the theoretical calculations were a huge success. But the work isn't over yet. The final step in any modern engineering project is to verify the result. You have to recreate the whole thing in a digital environment to prove this wasn't just a lucky break. Using some really powerful software called ANSYS Forming, the team built what's known as a digital twin of the experiment. It's basically a perfect virtual copy of the tools, the metal, and all the physics involved. The setup involves importing the exact shapes of the punch and die, defining the specific aluminum alloy, and setting the correct rolling direction. And, most importantly, you have to activate the software's springback calculation to mimic what happens in the real world. So after the simulation runs, the software produces its own version of the final bent part. This lets the team measure the angle just like they did with the real photograph. The final angle predicted by the simulation was 105.617 degrees. This is an incredible match with the physical experiment, and it proves the digital model is accurate. When you lay all three numbers out side by side, the target, the real-world result, and the digital simulation, the consistency is just undeniable. All three are within about half a degree of each other. This is the ultimate proof that the entire engineering model actually works. So, to wrap it all up, the winning formula for your own bending project is this. First, respect the material's properties, especially that rolling direction. Second, always do the math up front to calculate for springback. And third, use a digital simulation to validate your results. This really leaves us with a final thought. This powerful combination of theory, hands-on practice, and digital verification is way more than just a way to bend metal. It's the fundamental blueprint for modern engineering. It makes you wonder, what other complex challenges can be solved by following the same exact playbook? All right, for any of you heading into a manufacturing